Hello everyone. So we were studying the organometallics chapter, and we were particularly talking about the metal carbons and its uses. So in the last class, we studied what are the various techniques by which we can actually synthesize metal carbons. We saw that since metal carbons it acts as a precursor for various complexes, so the synthesis of metal carbons is quite important. Now, let us talk about a very famous reagent that is actually carbonyl based reagent, that is the Coleman's reagent, that has iron as the metal center and carbonyl as the ligand. Okay, and Na positive as the counter anion. So, actually, this reagent, the Coleman's reagent, has quite a lot of application in organic synthesis, as a lot of compounds you can functionalize using Coleman's reagent. Okay, so let us talk about all of these. So in figure 3.5, it is mentioned also, but let us draw and understand how exactly it forms this complex from the Coleman's reagent. So it is the iron-based reagent. Let me draw the reagent first, which has 4 carbonyl ligand. And in the coordination sphere, it has 2 minus charges. Okay, so for now, I'm just keeping it minus charges. There is counter anion, counter cation, which I'm not mentioning it over here. So when you react it with any halo compounds, okay, organic halogens, sorry, the X over here, then what will happen is that this negative charge, for example, I'm talking about how from this species is forming and this is forming. Okay, so this negative charge will attack on this R because of this electronegativity difference between R and X bond. So this electron will go to the X and with the X minus. Now this will actually get inside the coordination square and it will bind to the iron. So it is like this. Rest carbonyl is untouched. It is like this only. And it's in the coordination sphere as a result of attack of the negative one negative charge, only one negative charge remains. Okay, so that is what it is, right? So it is Na only because of only one negative charge, only one counter cation you have. Then you have one R as a ligand and 4 carbon as a ligand with middle center of iron. So this is exactly what is formed. And after that, when you give carbonyl group any further, then what happens is the migratory insertion of this carbonyl into this metal and R bond. So that exactly what happens in that we are going to study in just the next topic. This next topic that we are going to study is migratory insertion of carbons. For now, you understand this when you give carbonyl, then now this metal and this R, that is the alkyl chain, can insert this carbonyl within this, and it will form this type of complex. Okay, you can now again see this electron is as it is. There is no change in the electrode because anyways you are adding the neutral ligand into this, right? So there will be no change in the electron, the coordinated, like the electron at the coordinations complex. So this is how you can form this. Okay, for example, now if this is already formed, now what you can do is that if you treat this complex, the formed complex with acid, then you get the aldehyde. When you treat this with another molecule of organic halide, then you get the ketone. When you treat this molecule with some halogens like chlorine, iodine, bromine, then you get corresponding acid. Okay, and then like acid chloride or acid halides. And when you treat this with oxygen in the presence of acidic medium, then you get the corresponding acid. Okay, so these are the various uses of Coleman's reagent, and we saw that how important it is because you can actually form, starting from metal halides, you can actually form quite a lot of organic compounds like aldehydes, acids, acid chlorides, and ketones. So now let us talk about various steps that is involved when we're talking about metal carbons. So in the mechanism, there are a lot of steps. That, for example, here also we saw that like how this carbon is getting inserted in the metal alkyl bond. So all of these are various small steps that is involved in various mechanism wherever any metal carbonyl is present. Okay. So let us talk about all of these one by one. Migratory insertion of carbonyls. So the ability of the metal carbonyls, especially the metal carbonyl anion, to undergo migratory insertion has been utilized in organic synthesis. So for the preparation of acyl substituted metal carbonyls. Okay, so these are a good precursor for a host of carbonyl containing organic molecules. So if you want to make some organic molecules that has carbonyl unit in it, then such migratory insertion of carbonyl is very, very useful. It comes in handy. Here also you can see that migratory insertion is happening over here, right? And as a result of which, whatever compounds you're synthesizing has carbonyl unit in it. So that is what we are trying to see. Okay. So this equation 3.41 actually tells you what you need for this insertion of carbonyl to the metal alkyl bond. Okay, so this is a metal alkyl bond, and you need to put carbonyl inside this bond. So first of all, to make this process feasible, you need a lot of carbonyls, right? So if you give high pressure of carbonyl to it, then what will happen? This um, metal and this alkyl bond will break and carbonyl is going to insert. Okay, and it will form this acyl type of bond, okay, which we saw that which can further react with acid or some another alkyl halides or halogens or oxygen in the presence of some acid mediums can give you very important organic products that has carbonyl entity in it. So we already know that what is the importance of migratory insertion of carbonyls. Okay, so for all of this, you need some external carbonyl. Okay, now the next topic that we are going to study is the oxidative decarbonylation. So we already studied that when you have some metal carbonyl system, they are quite stable, right? So in order to make it reactive, you need to change something out of it. So you need to kick out a carbonyl from it. So how are you going to do it? Because since carbonyls are pi acid ligands, okay, so there is a double bond like character already happening in the system. So it is quite difficult to break such bonds, and obviously you know that the bond you are forming next is quite not that much stable in comparison to the metal carbonyl bond. So this whole process, it's quite difficult to happen, right? It's quite difficult to take place. How exactly it takes place, we are going to study now. So obviously you have a lot of metal carbonyls, and in order to make, like supposing you have a lot of metal carbonyls, or we are talking about homoleptic metal carbonyl complexes, in which in the metal complex you have only carbonyl as the ligands. But supposingly you want to substitute three carbonyls with a CP. For example, you can see in equation 3.42. This is what exactly they have done. So they actually had the homoleptic carbonyl complex of manganese. Okay, we know that it exists as a dimer with 5 carbonyl each with each metal center manganese. So you want supposingly to convert it into Cb manganese carbonyl whole tree. So you know that removing 3 carbonyl from a metal center is not an easy job. Or here actually 2 carbonyl, because each metal center only has 5 of them. So here it is very difficult job. You cannot actually directly react this metal precursor with Cp ligand and you can form this flow. You cannot do that, right? So for that you need some other source. For example, you need some, uh, actually what happens is that there is a formation of a carbonyl metal halides. Okay, if you form metal halides, then you can actually replace it. We can kick out other carbonyls. Okay, so now what is written over here? So carbonyl metal halides are prepared by oxidative decarbonylation. So this is oxidative decarbonylation. What does means? What does it mean, this word? So decarbonylation is very simple and straightforward. It means you are kicking out the carbonyl ligand. Okay, decarbonylation, you are removing carbonyl. But what is oxidative? So whenever there is oxidative or whenever there is reductive, all of these terms actually is telling about the oxidation state of the metal center. So for example, here the oxidation state of the metal center is 0. Okay, perhaps the oxidation state of the metal center in this entity after uh, treating with iodine is +1. So there is an oxidative process. So this whole process, the first process is oxidative process, right? So this is what oxidative, and also in the whole process, actually what you're doing is that you are For example, you're not here. Here there is no decarbonylation happening. Here it is just the breaking of the metal-metal bond. So you're introducing iodine and you're breaking this metal-metal bond. Let me draw it. So you have this metal center, and there's a bond. You have another metal center, and you have CO whole 5. Same over here in this metal also. So when you're treating it with iodine, then what is happening is that this bond is breaking, okay? And this bond is breaking, and you have I2 over here. So I'm actually doing the homo cleavage of this bond. It can be hetero as well. So this is breaking, and one, as a result of this, 2 molecules of this is formed, okay? It is written also over here. So in this process, there is an oxidation state change in the metal center. It is +1. It has lost 1 electron. Okay. So there is oxidation in of at the metal center. Now, since now the manganese is +1. Okay, here manganese was 0. So we already studied that when the oxidation state of metal is low, then in that case, metal carbonyl bonds are stronger. But as you increase the oxidation state of metal in the positive direction, like you remove electrons, start removing electron from the metal center, then what happens is that the back donation to the from metal to carbonyl decreases. As a result of which, the metal carbonyl bond strength decreases, and now decarbonylation is facile. So as a result of which, now decarbonylation is quite facile from this intermediate rather than this intermediate, just because here the oxidation state of manganese is +1 and here the oxidation state of manganese is 0. Now when you add sodium Cp, then actually it is negative, it is positive. Then in that case, you can remove 2 carbonyl, okay, and in iodine you can substitute with respect to the Cp, because Cp is better ligand than iodine, and Cp is a bulky ligand. It needs actually 3 coordinations pair in order to bind it. And the same example is given over here. You can actually activate this iron CO whole 5 also with iodine, and it can form this, and further you can get another XYZ ligand to substitute those ligands. Okay, so this we actually study how you can activate the metal carbonyl bond. Okay, so this is oxidative decarbonylation. Now another method is the photochemical substitution. So we are going to study that also. Okay, so photochemical substitution are the most common photoreactions in organometallic chemistry. Okay, kinetic studies have shown that the rate constant for the dissociation of one carbonyl unit which precedes the entrance of a new ligand is increased upon photochemical excitation by a factor of 10 to the power of 16 to 31, 32, quite a lot. That is so much, right? So this is a simple reaction. When you remove, like you don't consider this one, for example, for in the first place, you don't consider the H nu body for now. So what in this case, what is happening? There's a ligand substitution taking place. Okay, this is also L-type ligand. Carbonyl was also L-type ligand. So you are substituting one carbonyl with one phosphine. This doesn't seem facile, for sure not. The reasons are two. Even though the metal and the phosphine bonds are very strong, but in order to break the metal carbonyl bond is quite not easy. It's difficult, and also this PPH3 ligand is quite bulky, right? So there has to be some hindrance also taking place for say. So in order to make this reaction facile, we know that this equation 3.44, the reaction isn't facile, definitely not. But it is seen that when you add light or when you shine light to this reaction, then this reaction becomes quite facile and the rate of this reaction increases quite a lot. Okay, 10 to the power of 16 times, 32 times. So this makes it facile. And this is another example where they have used iron carbonyl complex and they have used this dialkene. Okay, so for this you need to knock out 2 carbonyl because it is 2 L-type ligands over here, and also it will form chelating type of a complex which is quite stable. But again, the same problem is that the decarbonylation is not that easy, and here you're not changing any oxidation state of the metal. Okay, the oxidation state of the metal remains 0 only, so which is even more difficult. So that is why you need to shine light. You're shining the light, and then this reaction is becoming faster. But here also there is one thing. So the photochemical substitution of the carbonyl by a monodentate ligand often results only in the displacement of one carbonyl unit. Okay, you cannot displace. For example, even if you are putting 2 mole of PPH3 unit over here, you will be unable to remove 2 carbonyl. Instead, you will only remove 1 carbonyl. Okay. So this is because the photochemical excitation of a metal carbonyl with the coordination sphere of a mixed substitution causes the dissociation of a ligand which is most weakly found in the ground state. Therefore, attempts to substitute a second carbonyl from any metal carbonyl sulfide X L species results in the displacement of L itself. For example, we know that the metal carbonyl is quite stable, and if you need here 2 PPH3 unit, which is quite difficult because as soon as you remove one carbonyl, you get 1 PPH3 here, and then again you want to remove another carbonyl, then that carbonyl is not going to be removed. Now PPH3 is only going to be removed because why is that so? Because the metal PPH3 bond is not that much stronger in comparison to the metal carbonyl bond. So if in the second place again you will shine light to this complex, you are not going to replace other carbon. Instead, only this PPH3 is going to be replaced. Okay, because that is less, the binding between the metal and the PPH3 is lesser in comparison to the binding between the constant between the metal and the carbon. So this is example. So here you have shining light, you have used THF, then one THF is there again, you're shining light, then what is happening? You're removing this THF. Nothing you're doing. You're not removing another carbon. No, you are not doing that. That is not happening. And here also, in case of this is POME whole thrice. Okay, here you can actually replace 6 carbons and get uh, you know 6 POME3 here, because the formed metal POME3 is this ligand, the metal and the metal, the bond strength between this metal and this ligand is stronger than that of carbonyl, and that is why you keep on shining the light. The one carbonyl is getting on replaced with the POME whole thrice ligand. That is why it is happening. All the substitution, all the carbonyls is getting substituted with this phosphine ligand. So if after the dissociation of the ligand, no suitable free ligands are present, the free coordination site generated through the photochemical dissociation of carbonyl may get closed by dimerization. The gap may also be filled externally by rearrangement of a ligand such as allyl or cyclopentyl from eta 1 to eta 3 or eta 3 to eta 5. Okay. So for example, here you are shining light to this ligand. What will happen? One carbonyl will go out, but you don't have any external metal. For example, here we have no other ligand. So what will happen? In order to get back to its like 18 electron species, what will happen is that if you have such ligands in the metal center, which is actually which has capacity greater than 1, okay, that can bind in a fashion which can increase or decrease its capacity, like CP ligand or this ligand. So now actually it is coordinated to 1, but now it can coordinate to 3, right? Right. So if you remove one carbonyl, then this metal can also bind 3 through this one also. So this is what is happening over here. Okay. The next what we are going to study after photochemical decarbonylation is the microwave assisted carbonyl substitution. So now we are going to study the microwave assisted carbonyl substitution. So we know that in thermal conditions also the substitution of carbonyl is quite difficult, but you can accelerate it in various ways. We saw that photochemically you can also accelerate it. Another way is the microwave assisted technique. So there also you can accelerate the substitution of carbonyls. So this reaction can be carried out in a dedicated microwave oven using Teflon reactor or a conventional oven fitted with a facility for inserting a water circulated reflux condenser. So basically, you need to carry out the reaction in the microwave conditions. So the reactions quite often proceed without the need of an inert atmosphere, are clean and give high yields. Okay, and it is also very fast because the microwave radiation is quite high in energy, right? So usually a solvent such as dikline or dikline PHF mixture is used. For example, the reaction of hexacarbonyl molybdenum with dicyclic pentadiene about simple one-step synthesis of CP molybdenum CO whole 3 whole twice. So it's a dimer. 94% healing in 1 hour. Have I told you? These microwave resistive reactions are quite fast. So you are getting 94% healing in one reaction, 1 hour only. So in contrast, when you use the conventional methods to synthesize the same compound, so it involves first of all the preparation of the sodium Cp and its reaction with molybdenum CO6, which gives this complex. Okay. After that, what you need is the oxidation with iron 3 ammonium sulfate or the preparation of metal CO whole thrice, acetonitrile whole thrice, and its reaction with freshly prepared C5H5, obtained by cracking of dichloropentadiene. So you see how difficult it was this reaction, but when you used the microwave assisted reaction, then this reaction became quite easier. Okay, so now you just have to cancel out various steps that is used in the conventional method in case of microwave assisted reaction. So here what you have to do is that you just have to take this mm, molybdenum whole CO whole 6 and then you have to treat it with dicyclopentadiene and under 750-watt microwave uh, condition using diclime as the solvent in 1 hour, you will get this timer 94%. So the microwave assisted method is also useful for high yield synthesis of a variety of cis substituted metal carbonyl whole 4 ligand L whole twice complexes from homoleptic octahedral metal carbonyl complexes just within an hour. So for that, what you have to do is that, so here what you learned is that maximum you can substitute 2 carbonyl. In the photochemical condition, maximum you can substitute only 1. Okay, in that case, that was only was the case when the metal and the L ligand that is formed is weaker than the metal carbonyl. That is most of the time is the case, right? But here also you can see that you can substitute 2 carbonyl with 2 ligands, or it can be basically it is only cis substitution happening. So even if it is monodentate, then also cis in the cis fashion only it will substitute. If it is kind of bidentate ligand, then obviously there is no other option other than cis coordination. So L can be piperidine, it can be pyridine, it can be phenanthroline, bipyridine. So L2 that means the bidentate ligands. So bipyridine and DPPE. Okay. So the metal carbon is over here. So we are going to study the metal nitrosyls, which actually behaves like carbonyl only. So that is why it is given in this chapter itself. Now, NO contains one more electron than the carbonyl in NO 5-star orbital. So we already studied now the carbonyl MO diagram. So let us revisit the metal carbonyl MO diagram. So this is the molecular orbital picture of the carbon monoxide. We saw here this the HOMO was the sigma, but we saw that for nitro, this ligand has one more electron than the CO. Okay, so that means that electron will be where? It will be here, right? So now there is the molecular orbital diagram of nitro is similar to that of carbonyl, but it has just one more electron in its pi star. Okay, so because of this difference, there is a difference in the chemistry, and that we are going to study now. So this nitrosyl contains one more electron than the carbonyl in its NO pi star orbital, and thus can act as a 3 electron donor, right? So 2 it is donating from the lone pair that was there in the carbonyl also, and 1 electron it has extra. So it can act as a 3 electron donor. Now in electron counting terms, 3 CO is equals to 2 NO, right? However, NO can act as a one electron donor when the lone pair resides on the nitrogen and the geometry is in the bent form. And in the oxidation state counting method, the ligand is viewed as a coordinated nitrogen ion like NO positive. So when in the linear form as a and as a coordinated NO minus when bent. Okay, we already saw in the last chapter that there is two binding forms of nitrogen ligands. The first is the N when the NO is in the positive form, and another is the NO is in the negative form. Okay, so when NO is in the positive form, then it is coordinated as the linear, and in that case, it can give 3 electrons. But when NO minus coordinates as NO negative, then in that case, the lone pair resides in the nitrogen. And here, in that case, it is a 1 electron donor itself. So it is 2 electron donor in both the forms. So it is a 2 electron donor in both the forms. So actually, it is 2 electron donor. It is set because of the what we can say is that here it is CO positive. Okay, you need to understand this. When the nitrogen is positive, then it is binding in the linear fashion, and it is a 3 electron donor. Fine. And another, that is when NO is coordinated as NO negative. In that case, it is the geometry is bent, and it is the 1 electron donor. Okay, you count 1 electron for NO minus and 3 electrons for NO positive. But you must see the electronic state, the oxidation state of all of these, the charges on the ligands. So it is NO plus. Then in any case, you have to subtract 1 ligand, right? I'll count it. So it will reduce to 2 electrons. And you need to add 1 electron also to the metal center, and that is why when you're talking about negative ligands, so it is 1, right? So it is negative over here. So you have to anyways add 1 electron in the metal sphere. So it becomes 1 becomes 2. So in both the cases, it is actually 2 electron donor. But in counting, when you're counting the electron contribution from the ligand, you count it as 3 and you count it as 1. The LX type and the X type. Although neither atom in the NO is a potential donor, neither nitrogen nor oxygen. The nitrogen atom coordinates preferentially, avoiding a large formal positive charge on the more electronegative oxygen atom. Nitrosyl complexes are readily formed by the replacement of carbon monoxide with nitric oxide. So when you treat your metal carbonyl complex with nitric oxide, then you can form the metal nitrosyl complexes. Only a few organometallic compounds containing nitrosyl ligands alone are known. So homoleptic metal nitrosyl complexes is not that much stable. That is why only few of them are known. But many mixed carbonyl nitrosyl complexes are formed, and it obeys 18 electron rule. They are very much known. Okay, so the mixture is known. Now, one problem in the synthesis of the nitrosyl complexes by direct reaction with NO is that excess nitric oxide at high temperature and pressure can cause unfavorable oxidation and decomposition. So, at high temperature and pressure, when you give excess of nitric oxide to the metal carbonyl, then there's a problem. There's a because their decomposition can also happen because it is quite very much reactive. So many current synthetic routes use reagents such as nitrosyl chloride, nitrites, and nitrosonium salts. So all of these reagents are used nowadays in order to form the metal nitrosyl complexes. And nowadays, a nitric oxide is not used as a source of nitrosyl ligands. Like carbonyl complexes, nitrosyl complexes are also characterized using IR spectroscopy. There you will have NO bond, right? NO stretching frequency. So the unpaired electron in the NO resides in the pi star antibonding orbit. We saw that. And it is easy to remove it to give NO positive. So as in NO positive PF6 minus. So NO positive is isoelectronic with CO. We know that if you remove 1 electron from NO, then you get the same electron as that of carbonyl, right? So infrared stretching frequencies of free NO is observed to be 1896. Free NO positive will be greater because you're removing an electron from the antibonding, that is making the bond strength between the NO N and O is even stronger, and that is why the stretching frequency is increased from 1896 to 2250 centimeter inverse. And the metal nitrosyl is the range of 1600 to 1900 centimeter inverse. Again, the bridging nitrosyl are also known. For example, Cp chromium NO fold twice Cl on treatment with sodium borohydride gives Cp chromium NO. One NO is terminal and another NO is the bridging ligand, and it is the dimer, it is whole two. Okay. So the terminal nitrosyl in these compounds are observed at 1672 centimeter inverse, while the bridging is observed as at lesser stretching frequency because of more electron donating by the metal, or we can say because of the more back bonding from two metal centers to the one single ligand. So there can be seen. So this is the linear fashion of nitrosyl ligand binding. The metal center, this is the bent fashion where the lone pair exists at the nitrogen. Okay. And then there is, and okay, it is a mixture. And then there is NO as the terminal as the bridged. Okay. We can see that when the NO is terminal, it is greater. When the NO is in the bridged fashion, then the bond strength or the stretching frequency is lesser. And the reason behind it is very much evident now. So this chapter, we are done with this chapter, and in the next chapter probably we'll be starting with the problems and the exercises. So I'll be dealing with all the problems and we are going to solve it, and I think it will be very much helpful. So this metal carbonyl chapter ends over here. It's a very important chapter when as far as organometallic chemistry is concerned. And in the next chapter, so we have in this chapter we saw two types of ligand. First was the carbonyl, and second in the last page we saw the nitrosyl, which is like carbonyl. And in the next chapter we are going to talk about other more ligands. So we are going to talk about some spectator ligands. So that are phosphines and N-heterocyclic carbenes. Again, so phosphines and N-heterocyclic carbenes after carbonyls are the most present, spectator ligands in various metal complexes. So that also makes them quite an important chapter. So till then, thank you, and the problems and the exercise will be solved in the next lecture. Thank you.